Yeah.
Okay, it seems that this started, so we are now to the last talk in the last session of ITRS workshop. It's a pleasure to introduce you Federico Olimpieri. He had got his PhD between Marseille and Rome. And actually, presently he is working in Paris at the LPN. He's interested in category theory and more precisely in the Lambeck view of carryover isomorphism. So a categorical view of formal systems and proof and types, correspondence, and especially in the case of intersection types and non-idempotent intersection types, he has worked on this family of type system, which is growing interest in the community, because ability of catching quantitative aspects of computations and reduction and so on. Okay, so I will start in a second his video. His talk is recorded, pre-recorded, and at the very end we shall meet again for the question and answer time. Does it start?
I cannot see it.
Neither me. Filter video. Well,
It should be filler video or video for live stream.
Hello, I'm Federico Olimpieri, and welcome to my talk on categorifying intersection types. I would like to thank the organizers for inviting me to speak here. The main goal of this talk is to give you some ideas about the possibility to develop a fruitful connection between two-dimensional categorical semantics and intersection type theories. I will start by recalling the standard connection. Hello, I'm Federico Olimpieri, and welcome to my talk on categorifying intersection types. I would like to thank the organizers for inviting me to speak here. The main goal of this talk is Hello, I'm Federico Olimpieri, and welcome to my talk on categorifying intersection types. I would like to thank the organizers for inviting me to speak here. The main goal of this talk is to give you some ideas about the possibility to develop a fruitful connection between two-dimensional categorical semantics and intersection type theories. I will start by recalling the standard connection between intersection types and categorical semantics, and briefly discuss how and why we can generalize it. Then I will present a two-dimensional categorical semantics induced by the bicategory of distributors. And in the third and last part, I will explain the relationship between these semantics and intersection type theories. Intersection types, as you know, you should probably know very well, were first introduced by Coppet design in the late 70s as an extension of simple type lambda calculus. You take simple type lambda calculus, you add an intersection connective A intersection B, an empty intersection omega, the idea being that your term is going to be typable with A intersection B whenever it is typable with both type A and B. The intersection type can be associative, commutative, or idempotent. If you do not impose idempotence in particular, your system becomes resource sensitive in the sense that the typing of your term can give you the exact number of times that the term is going to use its input during computation. These kind of type systems are very useful. They have been widely used to characterize normalization properties of programs, to talk about execution time of programs, to talk about lambda theory, lambda models, for instance. And a very nice feature of intersection type system is that they determine a very simple denotational semantics. Just take as the notation of your term the set of pairs gamma and A under which the term is typable, and this is preserved under reduction. An important example of intersection type system is the system R, independently introduced by Gardner and De Carvalho. And so it's a non-idempotent intersection type system. The intersection type is associative, commutative, but not idempotent. And it is a strict intersection type system in the sense that the intersection types does not appear independently, but only in the arrow type. And there is a very nice presentation of the intersection types in this system via a multiset construction. So this presentation has clearly a very strong semantic flavor and is going to be quite relevant for this talk. Then you have the standard rules of the system that are fairly well known in the intersection types community. And you can already see the resource sensitivity at the level of the variable rule, since the weakening can only be typed by the empty multisets, and the typed variable in the context can only contain one copy of its type. A classic result about system R is that typability in this system is equivalent to solvability. And system R is also strongly related with categorical semantics of linear logic lambda calculus given in the category of sets and relations. So object of our category are sets, morphisms between these sets are relations. And here, the intuitionistic arrow is given by the linear logic decomposition. So you have to consider the exponential modality of linear logic and the linear arrow. The exponential modality is built via the free commutative monoid construction over a set that in more mundane terms is just the multiset construction over the set. So you take your set and you define the set of all multisets over A. And then the linear arrow is just the product of sets. This model has a very nice syntactic presentation via the system R, so a non-idempotent intersection type system. And the idea goes as follows. Take an element of the intuitionistic arrow. This is a pair where the first component is a multiset of element of A and the second one is an element of B. So element of A and elements of B are types, and then the intersection type is given by the multiset construction and the arrow type by the pairing. This kind of syntactic presentation was studied, for instance, by Daniel De Carvalho, and it allows us to present the notation of a term as the following characteristic function that takes a context delta type A, returns 1 if M is typable under delta with A or 0 otherwise. So it is a test of typability semantics, if you want. And this is very nice and well. It has been widely applied and studied, but there is something missing from at least a strict proof theoretic point of view. That is, when you work with intersection types and type systems in general, typing derivation are at the heart of the thing. And here, the model, this categorical model, doesn't say anything about typing derivation. So if you switch to a more proof-relevant structure in this sense, that takes a context delta and a type A and returns all the typing derivation of M under the context with this type, this is clearly not a relation, so it's outside relational semantics, but it's not even a denotational semantics in general, because trivially typing derivation are not strictly preserved under reduction, but not even up to bijection, so not even up to bijection given a context and a type, so not even up to isomorphism. For this reason, if you want to consider typing derivation, you have to do it outside standard categorical semantics, and this is unsatisfactory. We want to fix this, and in fixing this, we will reach a very general semantic theory of intersection types. So we are going to do so via a categorification process. Categorification consists of replacing set theoretic notions with category theoretic ones. So sets are replaced by categories, functions between these sets are replaced by functors between these categories, and equations between sets become isomorphism between categories, while equations between functions become natural isomorphism between factors. In this context, relations are replaced by distributors or profunctors, and these replacements will allow us to pass from a proof-irrelevant test of typability semantics to finally a proof-relevant structure where all the typing derivation of M under a context with a type are taken into account up to an appropriate congruence. And this new information about typing derivation gives us also directly a new information, semantic information about a quantitative aspect, the type system, that is the amount of typing derivation and the context delta with a type A up to a congruence. And so in doing so, we follow the work of other researchers. So first, Méliès and Zeilberger gave a definition of type systems as functors, and building on that idea, Mazza, Pellissier, and Viard gave a general theory of intersection types rooted on the notion of operand, but their theory does not account for denotational semantics and subtyping, while Tsukada de Jong gave us bicategorical denotational semantics with an intersection type flavor in the fashion of rigid tailor expansion. So this is strictly connected to intersection types with a very nice application that is actually the amount of this different typing derivation under a context with a type up to an appropriate congruence gives you the number of reduction path of non-deterministic programs to normal form. But the work of Tsukada de Jong is restricted to a particular case in a non-deterministic lambda y calculus that is also eta expanded. So we want to actually synthesize this different point of view and get a very general approach to intersection types that is also a denotational semantics and can account also for subtyping of these intersection types. Now, we are doing so via categorification, that is about making things explicit. And we will reach a refinement and improvement of an important semantics of programs, that is the relational semantics. Then also a parametric syntactic presentation of abstract and esoteric models of lambda calculus induced by the bicategory of distributors. Then we are building a bridge between abstract categorical construction and concrete syntactic intersection type theories. And this syntactic presentation is also a general semantic theory of intersection types plus subtyping. So we can account for subtyping, actually for what I call categorical subtyping. And finally, also for denotational semantics that is now dynamic in the sense that if M reduces to N, the beta reduction is not validated by equality anymore, but by a coherent isomorphism. And this coherent isomorphism has a very nice dynamic interpretation as reduction of typing derivation. Okay. Now, the idea behind my work is that you have the standard relational setting where you have sets and relation plus your command, or if you want, you can generalize it to preorders and monotonic relation plus your command that gives you the exponential modality of linear logic, and it gives you also a particular notion of intersection types that is given by the multiset construction. So resources and intersection types are given by the multiset construction. Then if you have preorders, you have a standard notion of subtyping. And finally, a proof-irrelevant and static denotational semantics in the sense that it's a classic denotational semantics. If you categorify, you replace monotonic relation with distributors, then the comonad becomes a pseudo-monad, and this pseudo-monad again gives you the interpretation of the exponential modality of linear logic that is also strictly connected to the notion of intersection type that we are considering. So we pass from a multiset construction for intersection types to a list construction, but it's important to notice that while the list construction is not commutative, strictly commutative, we actually will have the possibility to make permutations on this list. So now commutativity and idempotency in our case becomes the possibility to perform operations over list, and this is what I call a categorical subtyping that is given by morphisms between these lists that are the operations that you can perform on this list, and we will finally reach a proof-relevant and dynamic denotational semantics. Relations between sets or multisets are subsets of the Cartesian product, and you can consider them as the characteristic function. If you take the characteristic function point of view, we can widely generalize it, replacing sets with small categories, and then the two elements Boolean algebra with the whole category of sets. You get the notion of distributors or profunctors, and indeed a distributor between A and B is a functor between the opted category of B times A to the whole category of sets. You have the standard composition of relation, and then you have composition of distributors. Then depends on what is called a QN formula. That is a very general categorical construction that in our case boils down to just disjoint unit, so a sum of sets up to a particular congruence that depends on general categorical construction. And distributor determine what is called the bicategories. bicategory is a two-dimensional categorical structure that consists of sets of objects that are called the zero cells, so standard objects. Then you have morphisms between these zero cells that are called one cells, and they are standard morphisms. But this morphism does not determine just a home set, but a home category. So you have also morphisms between these morphisms that are called true cells, that are these alpha and beta. And you can compose true cells. This is called a vertical composition. But you also have an horizontal composition of one cells and two cells. But in particular, this horizontal composition is now associative and unitary only up to coherent isomorphism. So bicategories are not just a two-dimensional categorical structure, but they are a weak categorical structure also, in the sense that associativity and identity for the horizontal composition is now only up to coherent isomorphism. Distributors determine bicategories as follows. Zero cells are small categories, one cells are distributors between these small categories, and two cells then are just natural transformation between these distributors that in particular are functors. The bicategory of distributors is compact closed, and it strictly generalizes what happens in the relational case, if you know a little bit about that. And if you take the interpretation of the multiplicative additive linear logic, you have that the tensor product is given by the product of small categories, and in the case of sets was just the product of sets. The linear exponential, so the linear arrow, is given by the compact closed structure, so you have to take into consideration the tensor product and an appropriate orthogonality relation, so a duality operation that is given in the context of distributor by the opposite category construction. So for distributors, it's non-trivial, while in the standard relational case, this was just the identity. So in the relational case, you had the fact that the tensor product is the same thing as the linear exponential, while in the distributor case, you can differentiate them because you are doing a non-trivial duality. And then the width of linear logic, that is the Cartesian product of your bicategory, is given by the coproduct of small categories. Catani and Wiskel first considered distributors in the context of the notational semantics. Now we have an interpretation of multiplicative additive linear logic. We want also an interpretation of the exponential modality of linear logic, since we want a model of lambda calculus in particular, and we want the exponential that gives us a notion of intersection types construction. And in the standard categorical semantics, the model of the exponential is given by an appropriate comonad. And we already saw that in the relational case, this comonad depends on an operation over sets, so an endofunctor on sets that gives the free commutative monoid construction, that is the multiset construction over your set. You can actually have also idempotency, in the sense that this construction we saw corresponds to a non-idempotent intersection type system. But if you switch from sets and relation to preorders and monotonic relation, you can also have an idempotent intersection type system. You have to take the free bounded mid semilattice, so the underlying preorder of the free bounded mid semilattice, and this is clearly idempotent. Now, we want to do something similar in the distributor case. So we start from a collection of two monads of a small category that model resource management. And all of these two monadic construction perform the following. So they take a small category and they build a free S monoidal strict category of array, where S monoidal means that it is a monoidal strict category that also satisfies some additional properties. And in particular, we are considering a linear resource monad, a semi-Cartesian or affine resource monad, a relevant one and a Cartesian one. The linear one has that the tensor product is also symmetric, while the affine one has the fact that the tensor model is symmetric, but also the unit of this tensor product is a terminal object. The relevant one has asymmetries and diagonals, while the Cartesian one has everything. And there is a very nice compact parametric representation of this construction. That is, all of this construction determine a category whose objects are just lists of element of A. So we are replacing multisets with lists. We are making things explicit. And indeed, now these lists are linked via morphisms and not just via identity or at most pre-order relation. And it is actually parametric in the sense that the kind of function between indices that determine the kind of morphism between lists that you can have depend on the structure of the resource model. So for instance, if you are linear, this is restricted to bijections. If you are affine, this is restricted to injections. If you are relevant, this is restricted to surjections. If you are Cartesian, this is general functions between the indices. Now, I'm going to give also some intuition, okay, about this morphism between lists that I already said that you have to think about them as operations on lists. So you have your bag of resources that is a list, okay, that is also your intersection type if you want, and you can perform operation on it. So if you are linear, you can only perform one kind of operation since you just have bijections over indices, that is shifting or permuting object in your list, so permuting resources. While if you are semi-Cartesian or affine, you can also delete, so you can erase resources. You have the possibility to have injections here, and then you can then delete because you have the possibility to project, okay, your tensor product. And if you are relevant, you can also copy since you have diagonals, and then surjections. And indeed, here you are making a copy and then a permutation. If you are Cartesian, you can perform all the operations described above. So we had a standard categorical setting where we considered a multi-set construction, and then there you could talk about strict commutativity, strict idempotence. Here, instead, this is replaced by an operational approach, in the sense that now you have different possible operation over a list. So you have that commutativity is replaced by the possibility to perform permutations. So you have a concrete explicit information, while idempotency is replaced by the fact that you can copy and delete stuff. But you don't have in particular an isomorphism between singleton A and the list AA. Okay, this is important. You can only copy and delete. So we have now an operational approach in this sense. Now we have our collection of resource monads over small categories. We want to lift them to distributors, and we do so following a general method introduced by Hure, Gambino, Allen, and Winskell. Then we get a parametric Kleisli bicategory, parametric over the resource monad S. You take the opposite bicategory of this that I call S-cat-sim, that is the S-categorical symmetric sequences bicategory. And this is a parametric generalization of another construction of Hure, Gambino, Allen, and Winskell, that is the bicategory of generalized species of structure. If you know a little bit about species of structure, then our model has a very strong combinatorial flavor, since we are talking about a generalization of combinatorial species. Now, I proved parametrically over the resource monad, so this is a once and for all theorem, that if the tensor product of your free construction is symmetric, then the S-cat-sim in particular is a Cartesian closed bicategory, and then in particular it's a model of simply type lambda calculus, a bicategorical model of simply type lambda calculus. So we have a family of abstract bicategorical models of simply type lambda calculus. We want also a model of untyped lambda calculus, and we want to see how all of this relates to intersection type theories. And then the first thing that we are going to do is to build a reflexive object that is a non-extensional model for lambda calculus. And algebraically, we work as follows. Take a small category A, and then you build this family of inductive family of small categories. Then you take the directed collimated over the integers. And for those of you who knows what happens when you build a reflexive object on the category of sets and relation, this is clearly a strict generalization of what happened there. There you just take the union that is indeed the directed collimated in particular case. Here you have to be more precise. And this construction actually is just a free algebra construction of an endofunctor, okay, over small categories. And the fact that it's a free algebra, you can lift the free algebra structure to distributors, and it gives you the fact that it's a reflexive object, but it is non-extensional. Okay, so you have no extensional model for lambda calculus. Now, what it is very interesting for us is that this abstract free algebra construction actually has a very nice syntactic presentation, has a category of intersection types. So the idea goes as follows. The object of this category are defined as follows. You take as atomic types the elements of the small category A, and then you build your arrow type using the intersection type as list construction over elements of the category. And then you also have morphisms between these intersection types, okay, that are what I call the categorical subtyping. So the operation that you can perform on this list, the witness of the subtyping relations, if you want. You have atomic subtyping that depends on the structure of A, and then you have the subtyping of the arrow type that, as you can see, strictly generalizes what happens in the standard rule for subtyping for the arrow. Indeed, it is contravariant on the left, but now you are giving a witness, so precise information about the operation that you are performing on the intersection types in general. And then you have the subtyping rule for lists that is given directly from the free construction depending on the resource monad. So this construction is parametric, not just on the small category A, but also on the resource monad you are considering. And from this parametric category of intersection types, we build on the right a parametric category of a parametric intersection type system that I call the system E, parametric over the resource monad S and the small category A. Actually, after building this parametric intersection type system for distributors, I decategorified it, and I actually discovered the possibility to do a parametric construction also for in the relational case. So there is a nice application of decategorification here. That's from the information from the more general model I obtained something nice about the standard one. And now in the relational case, this is a parametric of your comonad and a preorder. And the idea goes as follows, that if your comonad allows you to have a preorder of types that can subtype, for example, the empty multiset, then you can have non-trivial weakening, since you have projection, so the possibility to, okay, subtype the empty multiset. And then you also have this possibility to subtype at the level of the application rule. So the context, you can replace context by the subtyping relation. Now, when you categorify, you replace the subtyping requirement by the fact that you have to present a witness of this subtyping. So a precise morphism, a precise information about the operation that we are doing on lists. And indeed, it goes very similar, that in the sense that here, if you have the list as terminal object, then you can in particular have projections, and then you can have non-trivial weakening. And again, if you present a witness of subtyping at the level of the application, you can replace your context. And here, the sum of context is a concatenation of list pointwise, while in the relational case is sum of multisets pointwise. Now we have morphism between types, and actually we can define an action on typing derivation using this morphism. It goes as follows: take a morphism between a type A and a type A prime, and a morphism between a context delta prime and delta, okay, F and eta. And then you take your typing derivation of M, if your term M under delta and A, you can act on the left with F and on the right with eta, and you got a typing derivation of M, this time under delta prime and A prime. So notice the contravariance of the action of eta, and indeed the action of eta is a right action, while the action of F is a left action. Okay. Now, to give some intuition, consider this simple typing derivation of the identity. You are choosing a subtyping at the level of the leaf from A prime to A, and then you are acting with this morphism of arrows types, that is then an arrow morphism, that boils down to a left action on the side of the variable, okay, on the term side, and a right action on the context side. And indeed, right and left action, all of which boils down to pre and post composition. So the right action clearly gives the pre-composition since it is contravariant, and the left action the post composition. And this determines what we were looking for, so a typing derivation with the new typing that was B prime, singleton B prime, arrow B. Now, we have typing derivation. We have actions of morphisms of typing derivation. Naturally, we can define a factor that I call the S intersection type distributor of M. And indeed, finally, this distributor takes a context delta type A and returns all the typing derivation of M under this context with this type up to an appropriate congruence that depends on the structure of the model. So this congruence is quite relevant, and we are going to see later some examples of it to have some intuition on what is going on. And then I proved that the standard denotation of your term in this parametric Kleisli construction, so in this family of models, of bicategorical models or lambda calculus, is actually naturally isomorphic to intersection type distributors. And in this precise sense, intersection type distributors are the syntactic presentation of these abstract models. Then you also have the dynamic denotation of semantics, that is beta reduction, is validated by natural isomorphism between intersection type distributors. And I want to talk a little bit about that because I find it quite interesting what is going on. So natural transformation in our case boils down to a family of natural bijections, okay, indexed by a context and a type A. This means that if you have a context delta and a type A, you consider all the typing derivation, the equivalence classes of typing derivation of M under this context with this type. This is in bijection with all the typing derivation of N under the same context and the same type. And in particular, it's natural. It means that it behaves well with morphism actions. And we can see a very simple example to give some intuition, because this bijection is actually a reduction relation in this equivalence classes of type derivation. And indeed, take this typing derivation of the identity applied to Y. So the identity applied to Y clearly reduces to its normal form as Y. And this typing derivation where you chose subtyping, so categorical subtyping on the left, another one on the right. As you can see, you perform one step of beta reduction, and then you are composing the two. Okay, the two, you compose the two, and indeed this means that substitution corresponds very nicely to composition on the morphism side, and this validates the basic intuition of categorical semantics, that is, the substitution corresponds to composition. But now we are talking about composition of morphism information, and indeed you perform a beta reduction step, you substitution and composition of subtyping. Now, how this can determine a function, in particular a bijection? This is all thanks to the congruence. So the equivalence classes of P1 is sent to the equivalence classes of P2. So it's a very strong congruence that determines the fact that the reduction is actually a function when you instantiate it to two particular lambda terms and context delta and type A, and it is also a bijection in particular. Now, we were able to generalize classic results on the relational semantics that is in our family of models induced by distributors are actually sensible. So you have equivalence between the non-empty semantics in a precise sense and Head-Normalization. So our models are typeability in our intersection type system is the same as Head-Normalization, because we proved it using the fact that this abstract model can present it syntactically via intersection types, and using a classic candidates of reducibility technique. Then we did something similar for the case of normalization. We have to restrict clearly to positive types, that are types where the empty list appears only never appears in positive position. Okay. And then also to strong normalization, you have to restrict to an irrelevant resource monad, that is a resource monad that where you have weakening, so the possibility to delete resources. And in that case, you actually have the fact that if you take the plus, okay, the plus types that are the types where the list doesn't appear at all, the empty list, this is equivalent to strong normalization. Now, the two important special cases of our construction are the linear and the Cartesian one. So the linear one is a categorification of the standard system R, okay? And indeed, as you can see, weakening is only given by empty lists, while the typing of xi actually on the context can be different from the typing of xi on the term side, but the difference depends only on the subtyping that you are choosing, because you can still have only one copy of your type in the context. Then the lambda structure is completely straightforward. And on the application side, we already saw it. You can eventually subtype, okay, your context when you have a morphism either between a delta and the concatenation of the different contexts. So the Cartesian case instead is a categorification of the classic Coppe-Dezzani. So it is a categorification of the idempotent intersection types. But again, idempotency is replaced by the possibility to perform copying and deleting operations. Yes, as you can see, indeed you have that the list is a terminal object, so you have a terminal morphism, eventually non-trivial weakening, and in particular you also have projection, so you can have a much larger list for xi in the context, okay, than just the singleton of the type. And then on the application case, you can actually simplify the rule, since you can copy, you can delete. And for this reason, you can just copy the whole context, okay, when you apply the application. Now, I want to conclude by giving some intuition about what is going on with the congruence imposed by the models, because it's very important to determine the notational semantics. So first, I'm not going to give a formal definition of the congruence, okay, but just some examples to give an intuition about it. And the first example is this typing derivation of the identity applied to Z, and indeed, as you can see, the only difference between the typing derivation is that we are subtyping in a non-trivial way on the left, the first one, and on the right on the second one. Okay, so we have the identity on the right for the first one, and on the left for the second one. And the model tells us that actually you can consider them as the same typing derivation because the information at the end, so the subtyping information at the end is the same. And this is a nice family of examples that gives you the idea of how our model is destructing actually all the redundancy that is produced by the fact that we're switching from multisets to lists. And indeed, actually, there are too many typing derivation, and the model tells you that you can actually consider them as equal, because indeed, if you perform the same permutation on the function side on your application on the intersection type, so you are performing permutation with your permutation sigma, and again the same on the input, okay, all the inputs, so all the typing derivation of n. This is the same actually if you did nothing, because the order is preserved, okay, and the subtyping information is the same, the computational information is the same. And indeed, the model tells you, okay, consider them as equal. And there is a nice example that concerns the Cartesian case, so the categorification of the standard Coppe-Dezzani. That is, if you take a typing derivation that demands n times the same type A, and you give to it n times the same typing derivation of n, okay, this was the same as you just you just asked for one copy of your type A and then one input of your typing derivation row. And this is because you can copy stuff, okay? So you have a diagonal, you can contract your type. But again, idempotency here is about operation, okay? It's an operational flavor, so the possibility to copy and delete. And this works for all n, okay, for all integers n, clearly. Now, another nice example is about context, so what happens for congruence on context. And indeed, here you have a typing derivation of x applied to x, so about auto application. And the model tells you that since in the first one you chose to subtype at the application level, while at the leaf level you did nothing, so just the identity. In the second one, you chose to subtype at the leaf level, but not at the application one. And the model tells you, okay, the information is actually the same at the level of the typing of x in the context. So you can consider the two typing derivations as the same. Okay, so we achieved a categorification of a relevant class of intersection type system that is also a general semantic theory of intersection types that can account for subtyping, for proof relevance, for denotational semantics. And most of what I presented, you can find it in my leaks paper of this year. And then I also have a categorified semantic for untyped call by push value. This is a joint work with Giulio Guerrieri, and it was presented at CSL. But I also have a calculus of approximants in the sense of Taylor expansion. That is, there is a parametric resource calculus that corresponds by a carry-hour style corresponder to this intersection type theory that I presented. And this is for now unpublished, so I wrote it in my PhD thesis manuscript. And I'm actually studying the relationship between my models and the span model of Méliès, because distributors and span are quite closely related. And there is something subtle and interesting going on. And it is also a first step towards game semantics understanding of this, what is going on, so to relate these intersection types with some kind of game semantics. And I'm also considering the theories generated by our models. Clearly, we already saw it, our models are sensible. In particular, they generalize what happens in the relational case. So they probably have a very nice relationship with the BUM theory, for instance. But there are a lot of questions that are still open. And I believe that the relationship between these models and the BUM theory is maybe more natural than the standard relational semantics, since now you can consider truly the structure of typing derivation that is more naturally connected with the structure of finite approximants in the BUM trees. Okay, so thank you for your time.
Okay, we are live again.
Okay.
I think so. So I don't know whether people have heard my short presentation of Federico. What are his interests clear, I guess, from the presentation. He has been working in general on the carryover and Lambek correspondence from the point of view of types and logic and categories here especially. He's presently in Paris at the LIPM, and and he's working on this categorical view of the logic behind non-idempotent intersection types. So, are there questions? You can't see from chat.
Raise their hand to join the video conference if you want. There is a raise hand button.
Oh, there is a raise hand. No.
I don't see.
No.
The last entry in the chat is mine. I will delete because the video has now ended.
Okay, there is a question, I think.
Is there?
Yeah. Okay, so yes, indeed, there is the possibility to do this construction with proof nets and then experiments on proof nets. I didn't actually carry out the proof net construction for now, but I think that I actually believe that you can do that just in the same framework. You just need to switch from lambda calculus to proof net. There is something subtle about orthogonality. I'm actually working on that, studying the relationship between my model and the span model. And we are working on actually giving an interpretation of not just lambda calculus, but linear logic in general. And indeed, ways to also add orthogonality to your type intersection type system if you want. And okay, so yes, there is a way to do the construction. In this case, you don't need to have extra categorical properties just in the construction of your reflexive object. You have to add some stuff. And maybe then, if you want also a nice way to talk about orthogonality, you could switch from small categories to chiralities. I don't know if you know a little bit about that. It was a notion introduced by Paul-André Méliès, and it allows you to have a nice way to see orthogonality. But actually, you could do the same also, just considering small categories. But it's a nicer presentation. And what I want to see about also this is a work that I'm doing now in the context of spans, and so you have some nice differences between the distributors and spans. Since in the span model we are going to have that reduction is actually given by equivalence. So we are going to have that. It is okay. Now it's a question of by Giulio Guerrieri. It is not clear what a bicategorical model. Okay, it's more or less clear. Yes, indeed, it's not completely straightforward. It is clear what is a bicategorical compact closed structure. So what is a compact closed bicategory? So you can have models of linear logic given in the compact closed structure, that is, for instance, the one of distributors. What is the more general notion of star autonomy? I don't know if somebody actually brought down the definition, but should be quite straightforward from the one of compact closeness. So I think that you can say, yes, you have at least the notion of interpretation of MALL, so multiplicative additive linear logic. And for exponentials, it's a bit more subtle, but actually you just need to take a pseudo-comonad that is monoidal. The problem is that the definition of monoidality is very complicated in the bicategorical setting, but you can write it down if you want. Okay.
Any other questions? I have one. Can you figure out synthetic usage of your theory, in the sense that when you define the model in a suitable category, can you derive? It seems to me that you derive the rules from the model itself. Is it correct?
Yes, it is.
So if you are interested in certain specific features, you can start modeling in the categorical setting and then derive. And this ensures that the derived properties do hold.
Yes, I think so. I don't have a general argument for any property you could want, but so you had to you still have to carry out the construction in the model, and then you can have the answer. But in general, I believe that most of construction that you impose on intersection types can be modeled that way, but it's not clear to me. It's very difficult to impose it in all generality what is actually doable, feasible, or what is not, because it's all about making actually some kind of free construction and monoidal construction over small categories. And so the problem is that if this monoidal construction actually determines a pseudo-monad, and then this pseudo-monad can be actually lifted to distributors. So there is a question of distributivity laws about monads, and in all generality, so we cannot say it, if it is possible or not. For instance, I know that it's not possible to do this construction directly, imposing for the initial objects and co-Cartesian product. So if you want to do that, you have to take at the beginning the opposite by category. So you have to do an opposite construction, and then it works. But otherwise, you cannot do it directly. Indeed, there is a nice correspondence between the construction that I call Cartesian, that is the idempotent intersection types, and a construction by Zainab Galal that he called it Scott perfunctorial semantics, and her construction is actually equivalent to mine, but it's dual. It's equivalent by duality, and she considers the coproduct construction for the monad. So you have this. So both are possible, but actually they are equivalent via duality. So it's quite subtle, I think. And but for for more complicated things, I still don't know. I think you need to check each cost property, additional property that you want to impose on the intersection types. For instance, yes, you can do extensional models. This you can do because you just can take the terminal coalgebra of an appropriate endofactor on small categories, and this gives you an initial and terminal coalgebra means that it satisfies the Lambeck theorem, and then you got D that is isomorphic, actually adjoint, equivalent to D arrow D. Okay, so you have this equivalence between the two, so you can get also extensionality, and the construction is similar to what normally you do on intersection types in the relational case, but you have this also morphisms between these types.
Okay, thank you. Other questions? Don't see questions from the chat. Well, if no other questions are there, I think we can thank the speakers for I wish to thank Federico, the first, and all speakers.
Thank you for the invitation.
And thank you for the talk. And for the participation, since this is the last talk in the workshop, I wish to thank everybody, the speakers, people attending to the workshop, the organizers, and I wish to draw your attention to the fact that we are opening a call for post proceedings. So people that have submitted will have their paper in the post proceedings, possibly with some partial editing which has been asked by the referee. But we invite all people in the community to consider to send a paper. I will share my screen just a second to let you see. Here is the call, and you see the new deadline, which is the 1st October, and the remaining. All these are in the CFP entry in the webpage that you will find of the conference. Okay, so I stop the sharing. Timing is going. So thank you, everybody, and hope to see you in possibly, hopefully, in presence in the next edition of the workshop. Thank you again. I'm supposed to stop here. Maybe I will leave the room. Bye.